I'm going to talk on a new feature for texture. We got it working. New feature for texture shading to be able to do it by tiles. And so this image has nothing to do with texture shading, but this is Lisbon in the early 18th century, and I thought this was appropriate since I live in Portugal now. And this is in the National Tile Museum, which I sadly have not yet visited. Some of you may be using texture shading already. This has been out available for a while, but if you're not, a very brief overview. This is a sample of a digital elevation model for an area near Isabella Lake in the Southern Sierras, just plotting the elevations as a grayscale. So texture shading allows you to take that and turn it into something like this, where it brings out the details in the canyon and ridge structure. If you were to try to, instead of processing this as a single image, if you wanted to split this into tiles and process them separately, piece them back together, you end up with something like this. So it does not work the way you would want, and this is the problem that we're going to talk about how to fix. So why does this, or why would you want to do this? Why would you want to build it in tiles? Well, suppose you have a very large data set that maybe doesn't fit in memory. Perhaps you want to map at high resolution of an entire continent if you have good available data for that. So you would, of course, want to process that in separate tiles and piece them together. Or another thing that might happen is you might have some areas of high resolution and some of low resolution, and you want to piece those together. And so this would be a new feature that is not currently possible with the texture shading. Why make a large map in such a high resolution when if you display the map on your screen all at once, you can't see those details anyway. But if you zoom in, one of the features of texture shading I call scale invariance is that as you zoom in on the image, it retains the same character. You don't have to generalize the image each time. And I'll have a couple examples of that. So this would allow you to build that map of a continent and use it in a pan and zoom type slippy map with just zooming in that single image on the fly as you change the view. So here's an example from a previous talk I gave. This is San Gabriel Mountains in Los Angeles. It's a fairly large area, and if we zoom in on that boxed area, we get this, and you can see that the character where the major features are in higher contrast and the smaller features are in lesser contrast is retained as you zoom in on smaller areas. And so this is one of the advantages of texture shading and why you might want to make a large zoomable map, a single image. So why does this tiling problem occur? So it has to do with the fact that as we're generating the texture shaded image, at each pixel we're using information in the neighborhood around. Texture shading can be thought of as a relative elevation, where it's showing you how high or low is that pixel compared to things around it. But we're not just looking at a local neighborhood around it, we're looking at information out to larger areas, but with a different weighting. So we're emphasizing the nearby data and less so the far out data, but the data at larger distances is playing a role. So if you're working on a single tile, the value at each pixel is going to depend on some data that's actually in the neighboring tiles or even beyond that, which we don't have. So, and then when you work on the next tile over, you're going to have different data that's missing, and so you're going to have different effects, and that's why they're not matching at the edges. So we compare a few different image processing type algorithms and see what the influences of the pixels around. Hill shading is, for that you just need to compute the local slope at that pixel, so you just need the neighboring pixel next door to see what the slope is. And so any pixels more than one step away are not contributing to the result. And so for that reason, if you were to do a hill shading in the tiled mode, the only issue you're going to have is on the very edge pixels of the tile where their neighbors are in the next tile. Aside from that, there's not going to be an effect. So the tiling works well with hill shading. You might just, to eliminate the problems with that one single pixel row, you might just overlap the tiles a little bit, solves the problem. Another algorithm would be a Gaussian smoothing, where we have a bell curve weighting function. And again, the neighboring pixels out to, in this case, maybe 10 pixels out are having an influence on the value at that location. But beyond that, there's no effect. So there, again, you're going to have only a narrow band of edge effects around the edge of a tile. Now, texture shading, you would see from this diagram like this is not a problem. It's even dropping off more steeply than the Gaussian curve. But there's a couple reasons that's misleading. One is that the texture shading is what's being weighted here is not the elevations at the different points, but the difference between that point and the center point that you're interested in. So the nearby points tend to have small elevation differences, and so even though they're weighted more heavily, they're still not contributing a lot to the result. Whereas pixels farther out could have significant elevation differences, and so this is a little misleading in terms of how rapidly that drops off. The other issue is here, we're just looking at the effect of an individual pixel. But let's think about, let's pick a radius like 10 pixels or 20 pixels. Instead of looking at an individual pixel at 20 pixels out, let's look at the circle of all the pixels that are 20 pixels away and see how those contribute, because they may be colluding and drawing the results in the same direction. Let's say the point we're looking at is on a peak, then all that circle of points 20 pixels out is all going to be lower, and so they're all contributing together to affecting that result. So if we combine the effect of all the pixels at a given radius, then the curve doesn't drop off quite so sharply. The Gaussian curve still goes to 0 at about 10 pixels, but the texture shading, we have a little more of an issue now with the pixels farther out, but it still doesn't look so bad. But what we really like is to see if there's a cutoff point where we can say, for example, at 20 pixels, that we can guarantee that the combined contribution of all the data beyond 20 pixels out is not having an effect. And so if we were to do that graph and say, for each distance, what's the combined effect of all the data outside that distance? And if we can say that that's negligible, then we know we can safely exclude all that data. When we make that graph, now we can see we have a big problem. Whereas unlike the other two algorithms, the texture shading, the total contribution of the stuff outside of a given area is still quite large out to a long distance. And in this case, the percentages on the vertical axis are actually meaningful, so I put those in. And this is a fairly realistic example. So for example, here at 20 pixels out, the data beyond 20 pixels is still contributing 20% to that computation. And again, that might even be a low estimate because those pixels are going to have potentially larger elevation differences, also contributing more. And if we even go out to 100 pixels, we still have a 10% contribution from everything beyond that. So unlike the other algorithms, this is going to be a problem for the tiling because we do care about the stuff that's at a distance. So before going on further, I want to summarize the steps in the texture shading algorithm because this will help us to understand the rest of the presentation. So we start with an input DEM in a gridded data form. Fractional Laplacian is a fancy mathematical term for essentially applying that orange curve from the previous graphs to the delta elevations. There's a parameter that's variously called detail or texture that the user can set that determines how steeply that curve drops off, and that determines the trade-off between how much do you want to see the effect of things close by, which shows you the small features, versus the longer distances, which gives you more emphasis on the larger features. The output of the fractional Laplacian is not yet appropriate to turn into a grayscale. It gives you, for each pixel, a value from plus to minus infinity. And then we need to take those set of values and sort of look at what's the general spread, which is going to vary from map to map, and get an idea of how we want to scale those down into something to get us a black to white grayscale value. So that yellow box is going to determine that contrast adjustment to turn the raw texture data into the grayscale shaded image. And that yellow box is going to become important later on. And then again, the user can then make additional adjustments to the contrast and brightness if they choose. So if we were to try to solve this problem as simply as possible, the first thing we might notice about the tiles is that the brightness doesn't match. So in particular, the center tile is a little too bright compared to what we're looking for on the left, which is what you get if you process the whole image as a unit. And the reason for that is simple. It's because that tile is mostly in a valley. It's lower than the surrounding tiles. But when we process the tile by itself, it doesn't know that. It doesn't know that the tiles around are higher. It doesn't know that it should be a little bit darker. And so the brightness is a little too high. So we can attempt to find a brightness adjustment for each of the tiles and try to improve that, and we get something a little better. And the next thing that's a little more subtle, but we can see, is that the contrast is too high on some of the tiles, in particular the center one. If we compare the contrast on the right to the contrast on the left, it's a little bit higher on the right. And this is actually a very easy thing to fix in the software, because what we do, the contrast is being set by that yellow box, which on the right image is being done once for each of the tiles. It's computing a separate computation for each one. Well, what we can do is just, we can generate, maybe we don't have the memory to do the image on the left at high resolution, but we can generate a low resolution version of that as a preview image, sort of, and then run the contrast setting computation on that image and use that single value that then would apply to the whole image, use that on each of the tiles. And so that's very easy to do, and this is going to become part of the final algorithm. And that gets us to here. And so we're better, but we still have the edge problems, and this is mostly because the brightness adjustment that we did was a little oversimplistic. So we're going to find a way to replace that with something better. So what we're going to do is look at this as a puzzle where we have 4 boxes. We have 2 variables, low res and high res, and then across the top, tile-based versus seamless. And we have 2 of these pieces already. We have the one in the lower left is what we get processing things by tiles in high resolution and then piecing those together. And the one in the upper right is downsampling the DEM to something with lower resolution and processing that through the texture shading as a unit. We can then easily fill in the upper left box by just downsampling the high-res tiled version to a lower res, or alternatively by taking the our low-res DEM that we use to produce the upper right box and just running each of those, separating it into tiles and running each of those through texture shading with the same answer either way. And then we need to figure out how, from those 3, how can we guess what's in the 4th box. So we can, for example, we can look across the rows and we can say, what's the difference between the 2 images in the top? So the one on the left is each of the tiles is missing the information from the neighboring tiles because each tile was processed separately. The one on the right doesn't have that issue. So if we subtract them, we can see what information was missing from the one on the left. And then we can add that missing information to the high-res version at the bottom, because the missing information about the neighboring tiles, again, remember the graphs, the individual pixels are not the problem. It's when a group of pixels collude. And so we're interested in the information from the neighboring tiles, but we don't need that at high resolution. We just need to know sort of generally what's happening in that area. So doing the low resolution comparison at the top is going to be good enough to fix the bottom graph. So if we look at that in more detail, we'll take those two boxes from the top and look at what do we have to add to the one on the left to get the one on the right, just subtract them. And this is our missing context information for each tile. So this is similar to our brightness adjustment, except notice that it's not exactly uniform in each of the tiles. And this is the improvement that we're getting over the simple brightness adjustment. And then the contrast adjustment, again, has been already done as we did in the simple example. So then we take our high-res version. We add the same brightness adjustment. There's an extra step where we have to, because we can only add 2 images if they have the same size. So we have to take the low-res one and upsample to high-res. Very simple. And when we add those, we should get the answer that we're looking for. So, and this turns out this actually works. So I just got this working last Saturday, so I was very excited when it actually did what I hoped it would do. So, all right, and then we can do the same thing with the columns. So we can say, what's the difference between the top and the bottom? Both of those are tile-based, but the difference there is the top one is missing the high-resolution data. It's missing the high frequencies, the details. So if we were to subtract them, we would get those details, and then we can go and add those details to the seamless one on the top right, and hopefully get the high-resolution thing we want. So we take those 2 boxes on the left and put them horizontally, side by side, subtract them. We get now the detail information that's missing from the one on the left. If we take our seamless low-resolution version, add the missing high-res data, and then again, we should get the answer we want. So it turns out that both of those methods are going to give us the same answer, because all we're really doing is adding and subtracting things, and we're just adding and subtracting in a different order. And so that works out the same. So you can see the 2 formulas in the bottom right. We've just replaced C plus B with B plus C. It's the same thing. So in the end, it will depend on which way of doing it is a little more efficient in the software. And then we've solved our puzzle, and we have our solution that we want. So this is, on the right is the result from the new method. On the left is what we would get by processing the whole thing as a unit. And it's almost the same, except if we zoom in, we still do have some small edge effects, and that's because the upsampling is being done tile by tile, and we have that issue of being right on the pixels right on the border, like we talked about with the other algorithms. So this could presumably be fixed by overlapping the tiles a little bit, and that would generate a solution. So that's about the end of my talk. This is just to what this looks like when you add all the pieces together, including the upsampling, the downsampling, the conversion, the splitting into tiles and putting things back together. So this, yes, and notice again, importantly, the yellow box, there's only one of those, which is based on the full low-res thing versus doing that tile by tile, and that's one of the key things that's happening here. And the adding and subtracting is actually being done not on the images, but on the pre-grayscale conversion, which is what we want, because if we add and subtract images, we might end up with values that are outside the 0 to 255 range, and that wouldn't work. This is the appropriate way to do it. And then, so this is the method using the sort of row-based subtractions, and then this is what it would look like for the column-based. In this case, in the red box there in the upper left, we can actually swap the ordering of the upsampling and the fractional Laplacian to save one step. So this has all been implemented, but as I said, it just got done a few days ago, so it's not, unfortunately, ready for people to use just yet. It's just a prototype, but I have talked to Bernie Yenny, and he is interested in taking this and implementing it into Edward. So hopefully fairly soon, Bernie and I will be able to get that done, and this will be available for people to use. So I think that's the end. So thank you. Okay, so we have time for one question. Yes?
Great talk.
Thank
really
you.
Interesting. The one where you combine the low and low, and you got like what look like great pieces of paper with the edges curled out. Can you tell me anything from that about how far away you would have to move in order to not have this effect?
Well, it would, so the problem again is, so the question is, from this image, can you tell how far away you would not have this tiling effect? So it's actually going to depend on if this is still on a small area of a mountain range, let's say, where as you go out farther and farther, the elevation differences are still getting larger and larger, you're still going to have an effect as far out as that's occurring because of that. So it's really a matter of where does your terrain start to become more flat, as opposed to how many pixels or how many tiles, that sort of thing. Does that answer your question? Okay. All right. Thank you.